The objective of this project was to build a simple wing structure by following the standard engineering design process, which includes 4 main stages: conceptual design, preliminary design, detailed design, and acceptance and evaluation. If the final product could still be improved, the process will be repeated with the improved design. In our project, we designed different spas and we went through the 4 stages of the designing process. Then we tested it to see if it met the given requirements. Then we decided if it was the optimal design or if we should improve the design and go through the process again.
When looking at conceptual design, we needed to initially understand structural performance requirements, for example, bending, which involves tension and compression, as well as torsional resistance. We looked into multiple spar structures, such as triangular spar and rectangular spar. We realized that the rectangular spar had more resistance from external stresses and easier to build and test. Through our initial design, we used our Excel document to decide the best height and width for our spar, then tested them. We then started adding internal structures to our beam to increase the load it could stand, as well as the torsional resistance.
In the preliminary design stage, we used the Excel spreadsheet to carry out an analysis to determine which spar design has the best overall performance. In order to get the analysis working, we first studied the documents provided and applied the formulas of the beam theory in Excel for it to calculate and generate outcomes for the bending moments, direct stress, as well as the torsion compliance for the spar. Through the spreadsheet, we also adjusted the location of the spar within the rib to make sure it fit within the required rib size. We did multiple trials at this stage, trying out different values of the spar geometry to get a pass on the direct stress evaluation and torsional compliance, and finally obtain the best geometry that met the requirements while also achieving the minimum mass possible. The spreadsheet had been very useful to predict the performance of the possible spar design theoretically, and it helped us envision of what to expect during real-life testings in the lab.
We utilized SolidWorks to simulate loads and torsion on various spar designs. Using the data from the spreadsheet, we found ideal dimensions for the spar and implemented it into a tapered I-beam and our current double I-beam spar. This provided the maximum displacement of the beam, as well as how the stress is distributed across it, as well as give us an insight into the mass of each spar. Overall, however, SolidWorks has its limitations and cannot imitate every factor in the real world, such as the varying quality of the foam board and adhesive we used.
The acceptance and evaluation process is to test the design to see if it meets the requirements, and we could therefore decide if we should improve on the design or not.
Initially in our design process, we settled on a hollow square cross-section in order to reduce weight. However, after deformation testing, we realized the spar was not stiff enough and not strong enough to withstand a large load.
Area moment is higher when the material is further from the neutral axis, and therefore meaning less deflection and an increased bending strength.
As a result, we settled on an I-beam cross-section, as it had a much higher second moment of area for the amount of material used, which keeps the weight low, but was strong enough to match the requirements.
To conclude, we've learnt a great deal about design and ended up with a finished project. One improvement we could have made is our aerofoil shape. In Excel fit requirements, however in the lab, the gap for the spar and the edge of the aerofoil would have resulted in the structure being flimsy and unstable, so we had to create an allowance which resulted in it surpassing requirements. Also, our I-beam spar could have been improved by cutting holes in the spar to reduce weight. Time limitations prevented this. Our I-beam spar could withstand high stress and load, and the aerofoils were accurately cut to be as aerodynamic as possible in the lab. We've learnt the design process requires